Let me give you some hints on how to organize things a little bit in assignment 3. Organizing files and folders. Because this can be quite important when you work with big data like we typically do here now in metagenomics, to organize yourself in folders. Because otherwise it can become very sort of difficult to keep the overview, I think. So let me just make some suggestions here now. So let's say that you have completed assignment 2 and you have an assignment 2 folder somewhere under your home, right, on Orion. Inside this folder you should now have at least these 4 FASTA files with contigs. Because in assignment 2 you made some assembly of Illumina reads and of nanopore reads. This one with metaspades, right? This one with metafly. And notice I'm only talking about the Illumina contigs that you got from the raw data, not the FastP, because you actually had 6 files in assignment 2. But forget about those FastP pre-processed data now. We only consider the raw Illumina data and the raw nanopore data. So that's why it's only 4 contigs here now that I show. These are in the assignment 2 folder. And these were made from the reads that are in this courses folder up here. And they are still there, right? Under this address here, under this path. You will find the reads that you used to create these contigs. And you will need this now for assignment 3. So assignment 2 results, some of them, are needed for the assignment 3. So what you typically now do, you create yourself a new folder, assignment 3, right, under your home somewhere. I don't care where, but I assume you have a assignment 3 folder. You should now, inside this folder, create 4 subfolders like this. I think this is a good idea. And notice there's one subfolder here now for each of these 4 sets of contigs, right? Inside here you have number of contigs, many of them. Inside here you have also many contigs, and here and here. The very first thing you're going to do in assignment 3 is to simply just read the contigs from this file, keep only those who have length 1000 bases or more, and store in this folder here. Then you do exactly the same here, and this is something you do in R, right? R code. Reading this FASTA file, computing the length of each sequence, keeping only sequences of length 1000 or more, and save it here. Write FASTA out to this folder, right? And then you do exactly the same for this one, put in here, the same for this one, put in here, and the same for this one, put in here. So now you should have one contigs file in each of these 4 folders. And they are not copies from here because they are smaller, right? You throw away all the short contigs now, those shorter than 1000 bases. So the FASTA files you get in here should be much smaller actually than this here. Yeah, perhaps not so much smaller in memory because you throw away only short contigs and they are not so big. The next thing you're going to do in assignment 3 is to compute coverage per contig. Coverage per contig. See module 8 for how to do this. And my point is then you work in each of these folders separate, or you make the script here. At least I would do that, but you do the job for each of these 4 in turn, right? You don't need 4 scripts to do this. You can do more or less the same in all 4 cases with some variations, right? Because here you need to use the bow tie, these are Illumina data, right? These contigs are based on Illumina data. And then you must go up here to see where are the reads from sample A, right? For your data set. Take those reads, map to the config in here using bow tie. This is module 8 stuff. And then you do the computation of mean coverage and variance of coverage and so on, like it says in the assignment 3 document, and store it in here as an abundance file or coverage file. I think we call it abundance file. Yeah, it's a 4-column text file only, with 1 row for each config, and then the config name, sort of ID, then the length of the config, the mean coverage of the config, and the variance of the coverage of the config. So there are 4 columns. Yeah, and then you do exactly the same here. You can use exactly the same script. You just change some names, right? Use the B sample reads against the B sample contigs here. But the rest is same. Then do the same for nanopore, but now you have to switch from using bow tie to minimap 2. That's the only difference really, because now you need to use the nanopore reads from up here, right? The nanopore A sample reads against the nanopore A contigs in here, mapping with minimap 2. And then exactly the same here. And in all 4 cases, you should get this table or this small text file with a sort of a table with 4 columns stored separately in each of these folders, right? So after you have done this part of assignment 3, there should be 2 files in here, a config file and a small text file with this coverage results, and the same here, the same here, the same here. Okay, that's it for now, but this video I will extend next week when we are launching module 9, because then there will be some further things to do here. But try to do this here now and organize yourself. I think this could be a good way to do it, have it in separate folders. And then you have the scripts on up here, but you read and save to the different folders depending on which dataset you are working with. It's important that we always do it like this when we are trying to do when we have contigs from different samples. We should sort of treat them separately for some time, especially this coverage information, right? It's very important that you take the A sample reads, map against the A sample contigs and not against the B sample contigs, for instance, because these contigs are made from a different sample. And if you take the reads from a different sample up here and map, the results mean nothing, right? It's completely waste of effort, really. Yeah, at least for this context, they mean nothing. They may mean something in another context, but here you have to make sure that you map the reads from the same sample as you have contigs from all the time. All the time. Okay, see you next week then.